Okay. So we're going to talk about symmetry and concavity and points of inflections today. So the first thing we're going to talk about is symmetry. We have even odd symmetry. I put a poster up over there. I also put your domain rules poster up. So I'm going to kind of start. I don't know if I have room in here for all my posters, but we'll see. So the terms even odd describe the symmetry that exists for the graph of a function. The easiest way to kind of explain symmetry is that even reflects over the y-axis and odd rotates about the origin. All right, so before I get into all this other stuff, let's just look at these graphs right here. And I'll come back and talk about the other stuff in a second. We're just determining if the graph is even, odd, or neither. So for example 45, can you fold this guy in half and it reflect over the y-axis? No, it doesn't reflect over the y-axis. Can you rotate it about the origin?
Yes.
Yes. Now rotating is a little bit more hard to see visually. So the trick for rotating, okay, is if you take your paper and you flip it upside down, do you get the exact same graph?
Yes.
Yes. And so that's kind of how you can see if something is odd.
So we're going to set the wrong screen.
Yeah, so when you're doing the test and y'all are flipping your papers over, I'll know what you're doing. I think most people can kind of visually see like the even because you're used to doing the symmetry and like mirror image. The odd thing, I don't know, is just a little bit harder to see visually. So that's how you can do that. So if you flip it over, it has to be the exact same thing for it to be odd. And so we're going to say that this guy here is odd. Odd functions, not all the time, but most of the time are going to go through the origin. Not always, but most of the time they'll go through the origin. If they don't go through the origin, when you rotate it, it's not going to be symmetrical. And I'll kind of show you what I mean here in a second. All right, so let's go to 46. On 46, can you reflect it over the y-axis?
Yes.
Yes, and so this one would be even.
Can it be both?
It can be both. So can you rotate this one if you were to flip it over? Would it be the same thing? No. But yes, good question. It can be both. All right, so on 47, can you fold this one over the y-axis?
No.
No, you cannot. Can you rotate it about the origin?
No.
No. So this one's kind of tricky because when you have this graph and you flip it over, it does look really similar, but if you look at my little green dot that I put there, in my original graph, my green dot is to the right, and when I flipped it over, my green dot is now to the left. Do you see that? So that's why it's not odd. So that's why a lot of times, not always, but a lot of times, your point has to go through the origin, so then when you flip it over, it won't move. Okay.
So it's kind of a draw point.
Yes. At that, like, I mean, that's not your, it's like your starting point. You remember in Algebra 2, you always had that starting point. That's normally the one. It's normally at the origin unless it got shifted. That's kind of the one that you're looking at. So then this one would be neither. All right, so we're going to break the notes up today so it doesn't feel like I'm talking quite so much. So what I want you to do now is I want you to look at your homework, and you're going to do numbers 1 through 7. All right, you're just saying whether it's even, odd, or neither. Some of you that work fast might have time to do all of the questions that I give you. If you work slower, you at least get a little start on it. So you're going to start each section. All right, so I'm going to give you a little bit of time, and then I'm going to continue on the notes. And so we're going to kind of do that today. It's just a good day for it. And if you have questions, let me know. Hello.
Hello.
Good. Hey, since you're here, can I get Calculate 84 on my iPad?
That won't be us. You did put a ticket in, right?
I did put a ticket in.
So I did see that. We'll make sure Jeff looks at it.
Okay.
Because he's gonna have to push them out.
Perfect. I mean, it doesn't just about where this one is. I'm not really that particular about it.
You don't want it a little higher than that?
Would it be more helpful to have the TV higher? Like, can y'all not see over the people's heads? Like Cameron or Hannah? Like, I don't know. Are you good?
Yeah.
Maybe just like a hair higher, because
Yeah.
maybe just a hair higher.
All right. So just a few inches.
Yeah.
Okay, we can do that. We'll be back tomorrow.
Thanks.
Some of these are hard. I'm struggling.
For that even on.
So like, this one, you can't like, fold it because I'm only on this side. So it's
Right.
This one's gonna be neither, right?
Right.
Same thing with this one. This one's a neither.
Right.
This one's just even.
Mhm.
This one will be folded.
Even, neither. This one's gonna be neither, because, can I draw on this?
Yeah.
So like this point right here,
Mhm.
if you were to flip it upside down, you see how it's on top now?
Mhm.
Where originally it was on bottom.
Okay.
So that one would be neither.
So both of these are
This one's even. If you flip it upside down, you get the same graph. So that one's both.
both. Okay. And then this one.
Well, I guess you can't fold it up. Yeah, because I was just thinking of folding it on top of each other. So it's just odd.
This one both.
So we've got even, neither, even.
Alright, we just checked. Jeff should have pushed it down.
Oh, it's already
Day before.
Okay.
So if you just want to check real quick.
Yeah. I didn't know y'all could do that without like coming and.
Yeah, it's, as long as they're free, we can push them out to any device.
Oh, I do have it. Yay!
All right.
Thank you.
You're welcome.
I haven't even done that one. That's what I have.
You can flip it. Five is odd. I don't think it's.
Yeah. Because if you flip it over, it's the same thing. The dot is in the same spot. So yeah, 5. Okay.
Yeah, 5 is odd.
Okay.
So it does look weird, but if I take 5 and I flip it over, because this guy here is upside down, this guy's regular, so is it the exact same graph?
Yes.
Yeah. So that one will work. What about number 7?
It makes it a lot easier if you have two papers.
It does. Yes, both. 7 would be both, because you can fold it in half, and you can flip this over. So that one would be both. Okay, let's go to the next part here. All right, so the next part is algebraically determining if something is even or odd. So like hypothetically, but we don't have a calculator, we have this function, and we want to determine if we're even or odd. So if you plug in negative x into my function, it will spit out the original function if it's even. If you plug in negative x into your function and it spits out everything being opposite, the negative version of your function, it would be odd. All right, so down here, is that okay? Did y'all get that? Can I move? All right, so down here on 48, we are gonna plug in negative x into my function. And we're gonna simplify it. So what is the absolute value of negative x? X. All right, so then we're gonna look, does this guy equal the original function?
Yes.
Yes. So because it equals the original function, we can say that it is even.
So these can't be both.
They could.
One could.
Well, no, not these guys. Not if it was in y equals, yeah.
Yeah.
I'm gonna show you one that's both algebraically in a little bit. Mhm. All right, so then on this one here, we are gonna plug in negative x. What happens when you cube a negative?
Just turns into Or it stays a negative.
Yeah, it stays negative because negative, 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 still going to stay negative. All right, so now, does that guy match the original?
No.
No. Is everything opposite?
No.
No. So this one's, it's not everything's opposite, it's not all the same, so this would be a neither. So if it's odd, everything has to be opposite. So the x cubed is opposite, but this 3 stayed negative. So that's why we're going to say that this one is neither. All right, let's go over here to this last one. All right, so I'm going to plug in negative x. What is negative x cubed going to turn into? Negative x. And so I'm going to stick that negative in front of the 2 so it doesn't look like 2 minus. And then negative times x is going to just be negative x.
Would that be negative x? So it would be a positive x? Negative
Yes,
times negative.
yes, you're right. Negative, negative, so positive. Thank you.
Sounds odd.
Yes, so then this one would be odd because if you look, the x squared changes signs and this x will change signs. So every term will change signs. So we could say that this guy equals the negative version of y, and then that's the rule for odds. That kind of make sense? Okay, I'm gonna give you like 5-ish, 4-ish minutes to do the next 4 problems. So 8 through 11. And let me know if you get stuck or need help. No, the 5, just think negative 5 times will just be negative. It's like negative 1 to the 5th power. So the 5 is just negative x to the 5th.
Is it just the 4?
Yeah, just those 8 through 11. Yeah.
So,
9, do we treat it like we treated this, or do we just?
No, you're just plugging in negative x and you're seeing what happens. Yeah.
you get odd, even, even.
So we'll finish this entire homework if we can do it in this time span.
We can get most of it done, yeah.
You got like,
Yeah.
That'll be nice. So I have plenty of anatomy homework to do.
Yeah, some lessons are longer than others in here, but this one's not that bad. All right, we ready? Can I move on?
We have a test about it.
Next week.
Next week.
Okay,
First test.
now look at example 51 on your notes. The problem with 51 is that your guy is implicit. All right, it's not solved for y.
So we need to flip it.
Now, you could solve for y, but because the squared here, the y squared, that's going to make it kind of gross. So I think I'd rather just leave it like this. And what we're going to do to check for even and odd is we're going to use these little guys right here. All right. So in an even function, when you plug negative x in, you get regular y. Right? That's what this coordinate point is saying. And then the odd one is when you plug negative x in, you get negative y. All right. So let's kind of look down here at the algebra ones that I did right here. So, hello. When I plugged negative x into this even one, it equaled regular y, right? And when I plugged negative x into this one, it equaled the opposite version of y. And so what you can do is you can plug negative x in to the implicit forms, but instead of looking for opposites, you're just looking for the same thing. So I think it kind of makes sense. So let's look at this one. Now you normally wouldn't do this, but hypothetically, if I divided everything, if I divided everything by -1, I would get the original function. Does that make sense? So what that means is, if you're checking for even graphs, you're going to plug in -x, y. And if you're checking for odd graphs, you're plugging in -x, -y.
It's basically to do both.
You have to do both if it's implicit. But what you're looking for is you're looking for it to just simplify out to the original function. All right, so we're not looking for like opposites anymore because we're plugging in the opposite part into the function. Like we're plugging in the -y in the function. So it'll simplify out to just be the regular function. Does that make sense? Maybe? Let's try an example. All right, so on this one here, if I plugged in -x, I'm going to leave y alone because for even functions, the y does not get a negative. What happens with -x squared? Yeah, it just becomes x squared. All right, so is this guy the same thing as this guy? Yes, so we would say this one's even. But I also want to check for the odd. So I'm going to plug -x in, and I'm going to plug -y in. And so because I plugged -y in, I'm not looking for opposites anymore. I'm just looking for it to simplify out to the regular function. So this -x squared simplifies to x squared. The y squared simplifies to y squared. And the 6 is going to stay 6. So is this guy your original function? Yes. So this one is also odd. This would be a both situation. It's an even and an odd. It's probably some kind of circle. So if your function is given to you implicitly, you have to check them both. And you're plugging in coordinate points instead of just -x. Does the difference make sense? A little bit? Okay. I'm going to give you like 5 minutes to do, maybe 4 minutes to do the next 4. And then we're going to use the rest of the time to talk about concavity. make sure you're checking both even and odd. You have to check both if it's implicit. Yes, it could be neither.
What'd you get? Even odd. I just looked at them. Because if it has a square, it's gonna go back, and if it has a absolute, I don't even have to do anything. You should be able to look at it.
I don't know.
I second guessed myself, and then I checked it out. And I realized that was fine.
Negative, negative, so that turned into x squared plus y squared, so that one was even. And then you plug in negative, negative, and so it ended up being, but yeah, that's right. Is that the one you were?
Yeah, I just didn't know if that was.
I realized you could just look at them.
Yeah, then once you get, yeah, you can kind of start
Because it's just, if it's squared. it
making those
stays the same,
connections
yeah.
that, yes, the square will make the negative go away.
The square and absolute value.
Yeah, just make it positive.
So when you do a negative squared, it'll turn positive. So then that'll just be positive, and then, yep. Okay, so now this guy here, is that the same thing? So then it would be even. And then you do the same thing for the odd, you plug in the negative y.
I just looked at them.
Yeah, that's what mine looks like.
This is the only one because it had two X, it's not gonna X on Y right next to the trigger.
Not everyone does it in this one. Did you get?
I almost put myself up there, not like that number.
Okay,
I could have.
pause where you're at, it's okay if you, are not done. I wanna talk about concavity and give you some time to work on that. Alright, so an inflection point is where a curve changes concavity. Alright, so a point of inflection is where you change from being concave up to concave down. And concave up looks like something like this. The math definition for concavity is your slope is increasing. That is what defines something as being concave up. So if you think about your slopes at these like little points here, do you see how your slopes are increasing at all those points? I don't know. Your slope is increasing. But what I like to say when you're talking about concave up is it looks like a happy face or a bowl. Some people like to see the bowl.
I like the happy face.
And then concave down, your slope is decreasing. So if we're looking at those specific points, you know, that's positive, negative, steeper negative, steeper negative.
It's kind of sad.
That's where the math definition of concave down comes from. But I like to think about it just being a sad face. Or an umbrella. Some people see the umbrella.
I could see an umbrella, but I like something.
I'm a happy sad kind of person. All right, so what we're gonna do right here is we are going to determine the intervals where you are concave up and concave down. Now, if I'm talking about intervals, am I talking about the X or the Y values?
X.
The x. So anytime you're talking about intervals, we are talking about the x values. All right, so we are just using the x values. Now, if you are stating a point of inflection, you need the whole coordinate point, the x and the y. So it is a point, so that's why you need both. When you're talking about max and mins, remember, I would put a point, but technically the max is the y value, the x value is where it's at. But for points of inflection, it's the whole thing. All right, so the other thing about points of inflections, do that in a different color. And this is something that will help you kind of find them, is that they are going to be in between your extrema. All right, your points of inflection a lot of times are in between the extrema. It is not the extrema itself. It will not be a max or a min. So let's kind of highlight my graph right here. All right, so what am I doing first? Is this going to be concave down or concave up?
Concave up.
Concave up, because if you look here, make my dots a little bit smaller.
Smiley face.
It makes a little smiley face. It's crooked, but it's a smiley face.
Then you go down.
And then we're going to be concave down all the way to what number?
4.
The 3, yes. So that's why points of inflections are going to be in between. So it's only concave down all the way to 3. And then we're going to be concave up. So you see how that's another happy face?
I'm drawing eyes for all.
The eyes help. All right, so your points of inflection where you change concavity will be in between your extrema. And that's going to help you because a lot of times people want to go all the way to the max or all the way to the min because that's just what you're used to doing. But if you're talking about concavity, it's about halfway. All right, halfway in between those max and min points.
Let's see.
All right, so when we are stating where we are concave up, I'm going to say we're concave up from negative infinity all the way to what? Negative 0.5, the x value, negative 0.5. And then we're going to be concave down from negative 0.5 all the way to 3. And then we are going to be concave up from
3
to infinity. And then my point of inflections, those are these guys right here that are in the middle of your max and mins. So points of inflections are in between the max and mins. They'll never be the same thing. All right, so your point of inflection is going to be negative 0.5 comma negative 3 and 3 comma 1. So the whole coordinate points of inflections are x comma y. Concave up and concave down, those are x intervals. So they all look the same because they all look like, with parentheses around them, but they are representing different type of numbers. All right, so before I let you do your homework here, let's talk about 53. So 53 says the function, and it gives me this function here, 2x cubed plus 3x squared minus 12x minus 4 is shown at the right. The relative extrema are labeled, and I want to find the average between the high point and the low point to determine an approximate value for the point of inflection. All right, so this is just to reiterate that the max and the mins are not points of inflections. All right, your point of inflection will be somewhere halfway in between your max and min values. So on this one, we are estimating, we are approximating it. This is not the way that you can find the point of inflection. It's a way that you can get a pretty good approximation, all right? So I'm going to take my x value points and I'm gonna average them. All right, so what's one of my x value points? What's the x value of the max?
Negative 2.
What's the x value of the min? 1. So I'm going to add up my two x values. I'm going to divide them by 2. All right, so negative 1/2 is my estimated x value. Now you could take that x value and you can plug it into this guy if you want, But you also can just find the average of the y values because the point we're finding is an estimation. So we're not even finding the real thing. So I'm just finding an estimation. And I think it's easier to do average than to plug it into the formula. All right, so what's one of my y values? 16 plus negative 11 divided by 2, which is going to be 5/2. So my average point of inflection is going to be about negative 1/2, 5/2. About. It's an average, all right? But that's kind of a way that you can kind of average. So just to show you that the max and the mins are not your point of inflections, but your point of inflection will be somewhere halfway in between-ish. And if you look at your graph, it does kind of make sense. Like this point right here does kind of look like it's at negative 1/2 and at 2.5, which is 5/2. So you can kind of tell that that is kind of about where your point of inflection is. Okay, so let's look at the homework real fast. On 16 and 17, it says given the continuous function, determine how many inflection points would be found and show the approximate location. So all you're doing on these two guys is you are literally drawing points where your points of inflection would be. Like you're just drawing dots on your graph and telling me how many of them there are. Does that make sense? Okay. On this one right here, this is like the example we did on the notes. Name your points of inflection, name your intervals for concavity. And then 21, that one's kind of hard. Do your best on it. And if you get stuck, I'll probably end up doing this one before your quiz tomorrow. But I want you to give it a go first and try it yourself before I do it. But I'll probably go over that one. So if you get stuck on that one, it's not a huge deal. Everything else that you should be able to do. And then you've got like 6, 7, 8. You have like 8 minutes left in class, so you should probably be able to make pretty good headway on this. It's a one-day lesson. You have a quiz on Monday over it.